I introduce you to Harry, Alice and Zahra, who are students in the electrochemical outreach group, Ucell.
I'd like to shake your hands, but I understand you don't do that anymore. Well, now then, what have we got here? Do you need me to bring my washing up bowl of water?
We've actually brought our own bowl and a battery that we made at Ucell around the corner. I suppose this might look a bit different to the voltaic power you used, Mr. Nicholson.
Oh, gosh, yes. Do you know, even though it was in May 1800, 220 years ago, my memory of that day is still very, very clear. Yes, our battery was rather more rough and ready than this one. Of course, all we had to go on was Mr. Voltaire's letter explaining how to build it, using discs of copper, zinc, and wet paper. We got a friend to make it who built pianos.
Yeah, so ours are slightly more sophisticated today, but the basic components are the same. So instead of using zinc and copper discs like you did, we now have batteries that contain lithium-containing metal oxides and graphite. And the idea is that metals can produce electricity, and the bigger the difference between these metals, the more electricity you can produce. So here I have the copper and zinc that you used, and I can read how much electricity I'm going to get from these. Zahra, how much are we getting here?
0.5 volt.
Yeah. And now if we use the coin cell that I made in the lab that contains lithium and graphite, how much are we getting?
3 volts.
Yeah. So it's just about optimizing that difference.
Now, I understand that Humphrey Davy had a lot of success later on with this technique of electrolysis. But tell me, did you ever discover how the electricity causes the water to separate? And then second question, do you still find it useful today?
Yes, Faraday developed this technique quite extensively to explain the inner workings of electrochemical cells. Now we call this electrochemistry. It relates chemical reactions of metals with the transport of electrons, otherwise known as electricity. Now, as you may know, Volta referred to two metals often being paired together. These are commonly referred to as electrodes now. So we can repeat your experiment and show you some insight as to how this has developed over the last 2 centuries.
Okay, so I'm going to talk you through electrolysis, which, let's break down the word first. Electricity, lysis, which means to split in ancient Greek. So basically, all we're doing is we're splitting something with electricity, the something being water. So we don't have a bowl, but we do have a beaker full of water here. So like I said, we need water and we need a battery or electricity. So if I stick these wires into this bowl of water, if you see, nothing actually happens. This water isn't splitting into hydrogen or oxygen. So the reason for this is because the water splitting reaction is actually thermodynamically unfavorable, which is just fancy speak for saying you need a driving force. You need an extra little kick to get that reaction to start. And that kick basically comes from a catalyst. And as you discovered, platinum is a great catalyst for this reaction. So I'm going to redo this. Inside here, we've got platinum catalyst. And instead of using this beaker of water, I'm going to get this syringe. I'm going to fill it with water. You can see it's water in that syringe. I'm going to just take this little part out here and I'm going to inject some water into this device. Just a tiny bit of water in there. So that water that I've put into here, I'm going to split into hydrogen and oxygen gas. So like I said, we need electricity, which I'm going to get from this battery right here. So I'm just going to connect that up, red into red, black into black. And I'm going to turn that on. And what should happen is you should get hydrogen and oxygen coming out of here. But of course, those are gases, and there's gas all around us, so you probably can't actually see anything, especially since they're colorless gases. So if I just get this beaker of water again and stick these in there, can you see those bubbles?
Mm-hmm.
Can you see those bubbles? So those bubbles are basically hydrogen gas and oxygen gas. So what we've done there is we've successfully split the water that was inside here into hydrogen and oxygen. And that is electrolysis.
Fascinating, absolutely fascinating. But do you still find it useful today?
Electrolysis has been very useful indeed. As you know, Humphrey Davy pioneered the use of electrolysis to extract metals from ores. In fact, the lithium that we use in our batteries, that's how we first obtained it. Now we see electrolysis as useful to the environment to help combat global warming. It is the only way we can produce hydrogen in an environmentally friendly way. And we have great hopes of using this hydrogen to reduce our reliance on fossil fuels to power vehicles.
The fossil fuels and global warming, I'm afraid I'm not, I mean, can you explain to me how they're connected?
Now, I'm sure they weren't called fossil fuels back in the 1800s, but basically fuels such as oil and coal are formed from millions of years of animal and plant mass decomposing into the ground. Now, when we use that carbon-containing compound, it releases carbon dioxide into the atmosphere. Now, since the Industrial Revolution, we've been burning more of these fuels, so we've been releasing more carbon dioxide into the atmosphere. And carbon dioxide traps heat from the sun. This is termed global warming. All right. Do you remember the Thames freezing over in 1814?
Oh, absolutely, yes. We had a frost fair. We had stalls and dancing. It went on for 4 days. I seem to remember there was an elephant was drawn, was led across the ice at Blackfriars Bridge. Has the Thames frozen in recent years?
No, at least not in the last 200 years. These events don't happen anymore due to global warming.
Gosh, so you mean the Earth is warming up all over? Goodness me. Who could have foreseen such consequences of such a useful form of energy? But I mean, how's all that connected to electrolysis and hydrogen?
If we continue to use these carbon-containing fuels, it will mean us releasing more carbon dioxide, and that will bring serious threats to our way of life. We hope for hydrogen to provide as an energy source, as energy dense as gasoline. That way we can use this to power vehicles and carry around. And we hope that by using this hydrogen, we can reduce our reliance on fossil fuels. Now, we actually have a hydrogen fuel cell here, and we can show you how it operates. It's essentially the reverse of electrolysis.
So it's, as Harry just said, the reverse of electrolysis, and how Zahra was explaining earlier is that electrolysis requires a kick, some kind of energy to make it happen. And of course, fuel cells are the reverse of this process. So as long as we have the same basic components, hydrogen, oxygen, and some electrodes, then we can produce electricity spontaneously. So I'm going to talk you through how our fuel cell stack works here. So we have hydrogen gas that comes in through the back of our fuel cell stack, and it comes into our fuel cell stack here. And inside the fuel cell stack, the hydrogen gas is split up into hydrogen ions and electrons. Now, these electrons, as you know, when they flow, they produce electricity, and this electricity is really useful. So this electricity can be stored in the batteries that we have here, or used in any appliances that we can plug in here as well. Now, what happens to the hydrogen ions that we produced? The hydrogen ions travel across the fuel cell, and oxygen comes in from the air through the vents at the side, and these react together to produce water. And water is the only product of this reaction, so there's no carbon dioxide for global warming either.
By combining the use of electrolysis to produce hydrogen from renewable sources like the sun and wind, we can provide hydrogen and hopefully use this to power, replace fossil fuels, and beat climate change. And we have you to thank for starting us on this journey, Mr. Nicholson.
Well, thank you very much. Thank you. This has been so fascinating. It is very gratifying to know that electrolysis has been so useful and that it has got such potential.
Thank you. Thank you to Alice, Harry, and Zahra. And I think we have Keenan with us as well today on the webinar. So if anybody has any questions that they'd like to ask, I have two questions. One which came on Saturday, which was I think probably for Zahra or Keenan if they're here, which was how does the oxygen and hydrogen know to come out of separate tubes? If anyone can answer that one really quickly.
Yeah, I can answer that. Hello, everyone. So as Alice was just describing, in the fuel cell stack, the hydrogen and oxygen actually enter from completely different sides. And there's a membrane that separates the two. And the two reactions that occur, so the hydrogen reaction on one side and then the oxygen reaction on the other side, are split apart by this membrane. And this membrane stops any gas traveling between the two. So the hydrogen and oxygen always enter on separate sides and leave on those same sides.
Thank you. And I have another question. I don't know who will answer this. This was sent in by William Franklin, if you're watching. Has the problem of holding and gradually releasing the hydrogen been solved?
I can answer this one as well. So I think this is talking about the issue with hydrogen storage. So once you've made the hydrogen through electrolysis, and then you want to use that hydrogen on a car or a train that's using a fuel cell. So at the moment, the commercial uses are using tanks with high pressure. So you pump in the gas and pressurize it many, many times above atmospheric pressure, and you can fill up more and more into the tank. This obviously has an issue when you're taking a flammable gas like hydrogen and putting it under pressure. There's safety concerns. The benefit of the tanks is that they're covered in a carbon fiber coating, which is extremely strong, so it's not going to explode even on high impact or any issues, say a car crash. But there are many research institutions that are looking into different materials. So metal hydride forms can actually contain the hydrogen in the atomic structure. And this has the benefit of not needing the gas to be under high pressure. There's also lots of other materials like metal organic frameworks. The list goes on.
Thank you. I don't know if any of you listened to Women's Hour, not last Wednesday, I think the Wednesday before, they had on it the two ladies who are currently piloting a hydrogen powered train between Warwickshire and Worcestershire, and they were saying it would be another couple of years before they could get the bits to fit under a carriage. At the moment they're all in a carriage, aren't they? So I don't know, are there any other questions? Any easier ones? Oh, here we go. Here's one from Hassok. So Hassok says, fuel cells are nice, but you need electricity to generate the hydrogen. Will the UK have enough capacity to generate enough electricity from non-fossil fuel sources?
I think I can weigh in on this because it's more sort of comes into my sort of research field. So where Keenan's more on the fuel cell side in his PhD, I'm focusing on lithium-ion batteries. And so fuel cells are nice, but you need electricity to so fuel cells are what we use to convert from chemical energy to electrical energy. It's not so much that we generate our own electricity, we just convert from one form to another. And then, yeah, so we use batteries to store the energy. So if a fuel cell creates a certain amount of energy and you don't need it all at that one moment in time, you can store it in a battery and then come to it later. Do we have enough from non-fossil fuel sources? So I think I remember mentioning towards the end of that recorded clip from the park, how we're trying to combine electrolysis with renewable sources like the sun and wind. Do we have enough at the moment? Probably not, but we're trying to increase our efficiency when using things like the sun in solar cells, wind in wind turbines, and phase out our reliance on fossil fuels. So this is an area of research where there's a lot of pressure to sort of develop these and develop them fast, because we're sort of running out of time in the global warming challenge.
I think it's also worth mentioning that very recently the government announced a greater dedication to hydrogen dependency, and their main way of achieving this is through the wind in the North Sea, and up there with almost unlimited wind power, they could generate excessive amount of electricity, more than enough to generate enough hydrogen to power all the transport in the UK.
Yeah, and I think as a country as well, we might rely on wind energy more, in the sense solar cells would be more convenient in countries with more sunlight. So if you look at deserts in Arizona and America, they use a lot of solar cell systems in the Nevada desert and all that. But over here, you get them on some people's roofs, but it's not as efficient. Obviously, we've had a cloudy day today.
Thank you. Thank you. Has anyone got any other questions? Okay, I've got off lightly then. That's good. No, I don't need to worry about knowing my dates. Okay. So thank you, everybody, and I'm sorry it's late. And just again, huge thanks to the Friends of St George's Gardens who invited us, from Ian Brown, who pulled us all together. We didn't all meet until the first time we all met was on this Saturday. Jules Date, who I hope you agree was a really fabulous Mr. Nicholson, and Keenan, Harry, Alice and Zahra from Ucell, and everyone from the Bloomsbury Festival. Thank you very much. And thank you for sparing the time this afternoon, those of you that have attended. Thank you.